Hello everybody. So in this video we're going to continue with chapter 3, sequences and series, specifically section 3.4, series. So in common usage, the word series is the same as sequence, but in mathematics, a series is the sum of terms in a sequence. So for a sequence of values a sub n, the corresponding series is the sequence of S of n, with the sum being equal to the first term plus the second term all the way to the last term. So if the terms are an arithmetic sequence, then the sum is an arithmetic series. Now let's talk about sigma notation. Most of the series we consider in mathematics are infinite series. This is to emphasize that the series contains an infinite number of terms. Any sum in the series S sub k will be called a partial sum, and it is given by S of k is equal to a sub 1 plus the second term, so forth, until we reach the kth term. But for convenience, this partial sum can be written using sigma notation. So notice that the sum is equal to sigma notation from I equals 1 to k, and this would be the same as the partial sum that we saw just a little bit above. For example, suppose we measure the heights of 6 children. We will denote their heights by x1, x2, x3, x4, x5, and x6. So the sum of their heights would be x1 plus x2 plus x3, etc. But it is written more neatly using the sigma notation. So this would be the sum from I equals 1 to 6 of x sub I. Now, if we take the heights of the children to be x1 is equal to 112, x2 is equal to 96, x3 is equal to 120, etc., then the total height in centimeters is, again, using sigma notation, from k equals 1 to 6. Notice that it's just the sum of each of the terms. And since we already know what they are, all we have to do is add these numbers, 112 plus 96, 120, 132, 106, 120, and we get a total of 686 centimeters. Notice that we used k instead of I in the formula above. The I is what we call a dummy variable, so any letter can be used. So notice that these two are equivalent. We can use k equals 1 or I equals 1 with x sub k and x sub I. So next we have example 3.14, and it says write each series in full. So for A, we have the sum from I equals 1 to 5 of I to the 4. So this is simply going to be 1 to the 4 plus 2 to the 4 plus 3 to the 4 plus 4 to the 4 plus 5 to the 4. And we just leave it like that because all they're asking us to do is to write each series in full, not to solve it, right? So for B, we have sigma, so sum from R equals 3 to 7 of 3 to the R. So that means that we start at 3, so that would be 3 to the 3 plus 3 to the 4 plus 3 to the 5 plus 3 to the 6 plus 3 to the 7. Again, we don't solve it, we just leave it like that. And then for C, it says the partial sum from J equals 1 to N of X sub J times P of X sub J. So here we don't have a specific formula. That means that all we have to do really is just plug in the values. So I would say x1 times P of x1 plus x2 times P of x2 plus, and this just continues indefinitely until it reaches the nth term. So we would write the last term as x sub n times P of x sub n. So in example 3.15, they actually ask us to evaluate this partial sum from n equals 0 to 5 of 2 to the n. So then we would say, well, n equals 0 to 5 of 2 to the n. This would be 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4. plus 2 to the 5. And if we calculate that, it's going to give us 63. So next we have example 3.16, and it says write the sum 1/2 minus 2/3 plus 3/4 minus 4/5 all the way to 99 over 100 using sigma notation. So we have to use sigma notation, and let's assume that we start at k equals 1 because we see that there's a 1 here. And notice that we can see that the series increases 1 by 1 on the top, right, up until 99. So this means that from k equals 1 to 99. Now, there's another aspect of this series or this sum, and it's the fact that it's alternating signs. Notice that 1/2 is positive, then we have negative 2/3, then positive 3/4, then negative 4/5. So that means that there has to be a negative 1 multiplying the series with an exponent that we're going to decide on in a minute. Now, what would the expression be that generates 1/2, 2/3, 3/4, 4/5, etc.? Well, that could be something like k over k plus 1. So how about the exponent? Well, if we start with k, let's see if we do that. If we put a k here, it wouldn't work, and you'll see why in a second, because if we put k, for the first term, we would have negative 1, but the first term is positive, so we can use here k plus 1. And this should be the series using sigma notation. Okay, so next let's take a look at some properties of sigma notation. There are a number of useful results we can obtain when we use sigma notation. So number 1, for example, suppose we have a sum of constant terms. So notice that there's no variable here. It just says the sum from 1 to 5 of 2. So that just means adding 2 5 times. But that's the same as saying 5 times 2, which is 10. In general, if we sum a constant n times, then we can write it as n times k. So n is going to be the number of times we would be summing it, and k is the constant, so obviously this would be n times k. Now suppose we have, for number 2, the sum of a constant multiplied by I, for example, from 1 to 5, 5i. So that would be 5 times 1 plus 5 times 2 plus 5 times 3 plus 5 times 4 plus 5 times 5. But we can rewrite that as 5 times 1 plus 2 plus 3 plus 4 plus 5, right, if we factor out the 5, which is 75. But that is the same as saying 5 times sigma from 1 to 5 of I. So in general, we can say that if we have a constant multiplying I, it's the same as multiplying the constant times the I sum, as we can see here. So let's take a look at property number 3. And it says, suppose that we need to consider the summation of two different functions, such as the sum from k equals 1 to n of k squared plus k cubed. So this would be the same as 1 squared plus 1 cubed plus 2 squared plus 2 cubed, all the way to n squared plus n cubed. But we could rearrange this as 1 squared plus 2 squared all the way to n squared plus 1 cubed plus 2 cubed all the way to n cubed. So in other words, we can split these functions into two different sigma notations. Notice that we would have a sum of k squared from 1 to n, and then a sum of k cubed from 1 to n. So in general, if we have the sum of functions, we can just separate them into two different sums. For number 4, it says at times it is convenient to change powers. For example, notice here number 1, from 1 to k of a sub 1. So that would be a sub 1 plus a sub 2 all the way to a k minus 1 plus a sub k. And this would be the same. It's the same as saying the sum from I equals 0 to k minus 1 of a sub 1 plus 1. It would be exactly the same thing. So if we take a look at number 2, notice that this is the sum from I equals 1 to n of f of I. That would be the same as saying the sum from I equals 1 to k of f of I plus I equals k plus 1 to n of f of I. And notice that we could rearrange it as the sum of I equals k plus 1 to n is equal to the sum from I equals 1 to n of f of I minus the sum from I equals 1 to k of f of I. So now let's talk about arithmetic series. In arithmetic series, we're concerned with adding the terms of arithmetic sequences. It is very helpful to be able to find an easy expression for the partial sums of such a series. For example, find the partial sum for the first 50 terms of the series 3 plus 8 plus 13 plus 18, etc. Now, if we want to add those 50 terms, it would be a very long and tedious process, but we can do a trick. Notice, we know that the sum of the 50 terms is going to be 3 plus 8 plus 13 all the way to 248. Now, if we do a second sum, but backwards, so we would start with 248 and then come backwards, plus 243 plus 238 all the way down to 3, and then we add these two rows, notice that we're going to get twice the sum of the 50 terms in the series. And notice that if we add these numbers, they're all going to be 251. So that means that we would have 251 50 times. So what would be the solution to the sum? It would be 50 times 251, but divide that by 2, and we would get 6,275 as the partial sum of the 50 terms of the series. Now, this reasoning can be extended to any arithmetic series in order to develop a general formula for the nth partial sum of S sub n. So now we're going to generalize. Notice that the partial sum is equal to the first term plus the first term plus the common difference, plus the first term plus 2 times the common difference, and so forth, all the way to the end where it's the first term plus n minus 1 times the common difference. Now let's do the same, but backwards. We start with the last term. So a sub n plus a sub n minus d. So now what we're doing is that we're subtracting the common difference from the last term. And then a sub n minus 2d, and so forth until we get to a sub n minus n minus 1 times d. So what happens if we add these two rows? We're going to get that twice the sum. And notice that from here we get this, right? a1 plus an. And then this is going to cancel out. So we're going to get a1 plus an. This will cancel out. So we get again a1 plus an, and so forth, because in the last sum, this also cancels out. So what happens? That means that this repeats n times, right? Because there are n terms. So that means that we can reduce the expression above to this. 2 times the total partial sum is equal to n times a1 plus an. Now, we can reduce this to this, right? Because we can divide by 2. So the sum is n halves times a1 plus an. So let's change a little bit and notice that we can say that it's n times a1 plus an over 2. But we can substitute the nth term for the formula that we already know, right? Which is a1 plus n minus 1 times the common difference. So if we substitute that here, as we can see, we're going to get finally an alternative formula for the partial sum of an arithmetic sequence, which is n halves times 2 times the first term plus the number of terms minus 1 times d. So example 3.17 says, find the partial sum for the first 50 terms of the series 3 plus 8 plus 13 plus 18, etc. So let's remember that the formula we found is S sub n is equal to the total amount of terms divided by 2 times 2 times the first term plus the amount of terms minus 1 times the common difference. Okay, so how many terms do we have? 50. What's the common difference? Well, obviously here we can see that the common difference is 5, right? 3 plus 5 is 8, 8 plus 5 is 13, 13 plus 5 is 18. So that means that the partial sum for the first 50 terms is going to equal 50 over 2, and then 2 times 3 plus 49 times 5. And then if we do the math here, this is going to give us again 6,275. So next we have example 3.18, and it says you are given a sequence of figures as shown in the diagram. So we have P1, which is like a house figure, and then P2 is two houses put together. P3 is three houses put together. So letter A, P1 has 6 line segments. As we can see here, 1, 2, 3, 4, 5, 6. How many line segments are in P20? So in P2, notice that they share this segment. So that means that we're really only going to add 5, right? 1, 2, 3, 4, 5. And the same thing with P3. So that means that the common difference is 5. And this is obviously an arithmetic sequence. So how many line segments are in P20? Well, we would just have to use the formula for an arithmetic sequence. So this would be P20 is equal to the first term, which has 6 line segments. So 6 plus 20 minus 1 times the common difference of 5. So if we do the math here, this is going to give us 101. So that means that P20 has 101 segments. For B, they ask, is there a figure with 4,401 segments? If so, which one? If not, why not? So that means that we get a total of 4,401 segments when we go 6 plus n minus 1 times 5. So we have to solve this for n, and if we get a whole number, then it does exist. So this would be the same as saying 4,401 minus 6 divided by 5, and then plus 1. So this would equal n. And if we do the math, this is going to equal 880. So it does mean it exists, and it would be the 880th figure. Okay, so for C, it says find the total number of line segments in the first 880 figure. So this is a sum, which is not the same as finding the total amount of segments in the 20th figure, right? This would be summing them all. So this is a series. Okay, so for that, we would apply the formula for the series. So S of 880 would equal 880 divided by 2, and this times the first term times 2, plus 880 minus 1 times the common difference, which is 5. And if we do the math here, it's going to give us 1,939,080. So next we're going to talk about geometric series. As is the case with an arithmetic series, in several cases it is desirable to find a general expression for the nth partial sum of a geometric series. So we start with an example. It says find the partial sum for the first 20 terms of the series 3 plus 6 plus 12 plus 24, etc. So this is obviously a geometric series where the common ratio is equal to 2. So the common ratio is equal to 2, right? 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, etc. So for this, we can express the sum of the first 20 terms in the series in two different ways and then subtract them. So first, we just write the terms of the sum, right? 3 plus 6 plus 12, all the way to the last term, which is this number here. Now, what if we do 2 times? Now, this is the ratio, right? 2 times the first one. Well, we would get the second term first, right? 6, because 2 times 3 is 6. Then we would get 12. And we would get the same ones repeated except for the last one, which would be 2 times the last term. Now we subtract them. If we subtract these two rows, right? This row and this row, we're going to get minus the sum of S20 is going to equal 3, because 3 minus 0 is 3. And then 0 minus this would be negative 3,145,728. So if we subtract this, we're going to get negative 3,145,725, but because we have a negative sign here, then this is positive. So this would be the total sum. Now we're going to use this reasoning and extend it to any geometric series in order to develop a formula for the nth partial sum. So notice that here we have this expressed in general terms. So the sum of the series would be a1 plus a2 plus a3 all the way to a sub n minus 1 plus a sub n, the last term. Now if we grab the ratio, the common ratio, and multiply it by the first series, we're going to get r times a1 plus r times a2 plus r times a3 and so forth. But notice that r times a1 is simply the second term. R times a2 is the third term and so forth. So we're going to get this, right? We're going to get the term before the last one, the last term, and one extra term. So now what happens if we subtract these two? Well, notice that this is going to cancel out with this will cancel out with this will cancel out with this, and this will cancel out with this. So we would only be left with the first term and the last term in the second series. So notice that this is the same as saying S sub n minus r times S sub n, as we see here. And then we get the first term minus the ratio times the last term. So if we rearrange this, notice that we have a common factor here. S sub n times 1 minus r is equal to the first term minus the ratio times the last term. So if we rearrange it, we get this, right? We get this. Of course, r cannot equal 1, otherwise it would be undefined. We can substitute this expression, a sub n, so r times a sub n, we can substitute a sub n for the definition of the nth term of a geometric sequence. So notice that we have substituted that here. The nth term in a geometric sequence is the first term times the common ratio to the power of the index minus 1. So notice that we can rewrite this as a sub 1 minus, and notice that if we have r times r to the power of n minus 1, this is simply going to be equal to r to the n, because this is like having a 1, and if we add the exponents, we end up with r to the n. So this is the same as a sub 1 minus a sub 1 r to the n. And then we take out a common factor, and we finally arrive to the formula for the sum of n terms in a geometric sequence. So in example 3.19, they ask us to find the partial sum for the first 20 terms of the series 3 plus 6 plus 12 plus 24. So what would be the common ratio here? Well, 2, right? And then let's recall that the formula for the partial sum of a geometric series is equal to the first term times 1 minus the common ratio to the power of n divided by 1 minus r. So we have the common ratio, we have the first term, and they want us to find the first 20 terms. So that would mean the sum of the first 20 terms is going to equal 3 times 1 minus 2 to the power of 20, and this over 1 minus 2. And notice that this is going to give us, if we plug it in the calculator, it's going to give us 3,145,725. So now let's talk about the case of an infinite geometric series. So here they give us an example, and it says consider the series from k equals 1 to n of 2 times 1/2 to the power of k minus 1. So this would equal 2 plus 1 plus 1/2 plus 1/4 plus 1/8 and so forth, right? So what happens if we do a partial sum with n equal to 10? Well, that would give us a number like 3.996. If we do it with 20, then we would get a number like 3.99996. If we do it with 100, we get much closer to the number 4. So this implies something that we're going to see next. So as we saw in the previous slide, as the number of terms increases, the partial sum appears to be approaching the number 4. This is no coincidence. In the language of limits, we would say the following. the limit as n approaches infinity of this partial sum, or this infinite sum, I should say now, is equal to the limit as n approaches infinity of 2 times 1 minus 1/2 to the k over 1 minus 1/2. Now, what happens as k tends to infinity for 1/2? Well, that means that we would be dividing 1 by an ever larger number. If you divide 1 by very large numbers, you get closer and closer to 0, which is what we see here. The limit as n approaches infinity of 1/2 to the power of n is 0. So if you do the math, you end up with 4. In other words, we say that a series converges to L, and it is convenient to define L as the sum of the infinite series. And we use this notation. The limit as n approaches infinity of k equals 1 to n of a sub k is L. If the series does not have a limit, then it diverges. So in general, and we can skip this part here, in general, if the absolute value of the common ratio is less than 1, then what's going to happen is that as n approaches infinity, r to the power of n is going to equal 0. So if that is the case, notice that if we do the limit to infinity of the previous formula for a partial sum, this would tend to 0. Therefore, the sum of an infinite convergent geometric sequence is equal to this first term divided by 1 minus the common ratio. So now let's do example 3.20, and it says a rational number is a number that can be expressed as a quotient of two integers. Show that 0.6666 is a rational number. Okay, so let's look at this as a sequence. Now notice that we can express 0.6 with that dash on top. This is the same as saying 0.6 plus 0.06 plus 0.006, etc., right? Okay, but notice that this is the same as saying 6 over 10 plus 6 over 100 plus 6 over 1000, etc., right? So how can we express this in a different way? Notice that this is the same as saying 6 over 10 plus 6 over 10 times 1 over 10 plus 6 over 10 times 1 over 10 squared, and so forth. So notice that we have a common ratio of 1/10, right? R would be 1/10. And because R is less than 1, then that means that this infinite series would converge, right? So that means that 0.6 with 6 repeating indefinitely is going to equal the first term, so 6 over 10, divided by 1 minus the common ratio. And then if we do the math here, we're going to get 6 over 10 times 10 over 9. This cancels out. We get 6 over 9, and this is the same as 2/3. So we have proven that 0.6666 is a rational number, and because it can be expressed as the quotient of the integers 2 and 3. So next we have example 3.21, and it says a ball has elasticity such that on each bounce, it bounces to 80% of its previous height. Find the total vertical distance traveled down and up by this ball when it is dropped from a height of 3 meters and is allowed to keep bouncing until it comes to rest. Ignore friction and air resistance. So let's take a look at a picture of the situation. So notice that what they're doing here is dropping the ball first, right? It says the ball is dropped, right here, dropped from a height of 3 meters. So here, that means that first the ball drops 3 meters. Then after that, we have to consider that it's going to bounce up and then back down. So that means that we would have to multiply the following by 2. So first it would bounce 2.4 meters. but then after that, 80% of that, right? So that means 2.4 times 0.8. But it's going to be bouncing 80% of that. So that means that it's going to be plus 2.4 times 0.8 squared, and so forth. So what does this tell us? Well, what it means is that we have something like this, 3 plus 2 times L. Let's call it L, where L, because it says it is allowed to keep bouncing until it comes to rest. So this would be an infinite geometric series, right? So L is equal to the first term, 2.4, divided by 1 minus the common ratio, which is 0.8, and this is going to equal 12. So that means that the total vertical distance is going to equal 3 plus 2 times 12, right? And this is going to be 27 meters. So next we're going to look at applications of series to compound interest calculations. And we start with annuities. An annuity is a sequence of equal periodic payments. If you're saving money by depositing the same amount at the end of each compounding period, the annuity is called an ordinary annuity. Using geometric series, you can calculate the future value of this annuity, which is the amount of money you have after making the last payment. So let's say you invest 1,000 euros at the end of each year for 10 years at a fixed annual interest rate of 6%, as shown in table 3.3. So you start in year 10 with 1,000, the next year you deposit another 1,000, and here you get the future value. So notice that in general, we could say that the future value is going to equal 1,000 for the first year, plus 1,000 times 1 plus 0.06, which is 6%. And then this process repeats because next year it's going to be 1,000 again, but this time times 1 plus 0.06 squared, and then so forth, right? Until we get to 1,000 times 1 plus 0.06 to the power of 9. 1,000 is the first term, so this is the first term. So we could find the partial sum by applying the formula. Then we know that the future value of the investment is going to be first term, 1,000, times 1 minus the common ratio, which in this case is 1 plus 0.06 to the power of the amount of terms. So in this case, we have 10 terms, right? Because we have to consider this as the first term. And this divided by 1 minus the rate, right? So 1 minus 1 plus 0.06. So we plug this into the calculator, and we're going to get that the total amount after 10 years is going to be 13,180.79 euros. So now we can generalize the previous formula in the same manner. So let's take a look at table 3.4. So here we have the periods, right? M, then M minus 1, M minus 2, all the way to 1. Here's the amount invested, which we use R for. So notice that the first year we have R, the second year it's going to be R times 1 plus I, and then R times 1 plus I squared, and so forth until we get R times 1 plus I to the power of M minus 1. So notice that the future value is the sum of the entries in the last column, right? So the future value is going to be R plus R times 1 plus I plus R times 1 plus I squared, all the way to R times 1 plus I to the power of M minus 1. So that means that this is a partial sum of a geometric sequence with M terms and R, or the common ratio, as 1 plus I, right, the interest rate. So that means that we can summarize this as first term times 1 minus the ratio to the power of m over 1 minus the ratio. And then if we do the math here, notice that this is just going to be minus I in the bottom. And if we take out r as a common factor for the top, then we're going to get this expression that you see here. So now we're going to look at a different case. If the payment is made at the beginning of the period rather than at the end, then the annuity is called an annuity due, and the future value after m periods will be slightly different. So previously we were doing ordinary annuity where you make the deposit at the end of the period. So notice that the main difference here is that you're going to pick up an interest at the end of the first year. So in the first period you deposit R, right? But you're going to get a future value of R times 1 plus I. Then the next year you're going to get this, the following year you get this, the next year you get this, and so forth. So that means that the final value is going to change a little bit because the first term of the sequence is not going to be R by itself, but R times 1 plus I. And then we always reach the value, in this case, of R times 1 plus I to the power of m, and not m minus 1 as happened previously. So this is still a partial sum of a geometric series with m terms, right? So the first term is going to be R times 1 plus I, right? That was the first term. The common ratio is still 1 plus I, as we can see here. So the geometric series sum is going to be R times 1 plus I times 1 minus the common ratio to the power of m. And this over 1 minus 1 plus I. So notice that in the denominator we get minus I. And then here we can simplify this a little bit. Notice that we have 1 plus I minus 1 plus I to the power of m plus I. But notice that we can rearrange this by separating this and getting minus 1, right? Because if we do I over negative I, that's minus 1. So this formula is partially different because, again, of the fact that the deposit or payment is made at the beginning of the period. So for the first period, you do get interest. So notice that here we're testing the same formula, and this parenthesis is wrong. This parenthesis should be here, not here. So notice that here we're doing the same deposit of 1,000, but at the end of the period, you're going to get slightly more, obviously, right? Because you have that interest of the first year. So instead of 13,180 point something, then in this case, you would get 13,971.64 euros.